Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question raw and uncut. So we have another hard today, back-to-back hard. So the question is called apply operations to maximize score. So we have some arrays. We're not some arrays. We have an array of nums. And yeah, so it is 100k long. Each of the elements are also they're positive and they're like the maximum number is like 100k. And then we also have an int k, and so it's basically just an int or whatever this is here, which is like, so it is like somehow related to the length. But yeah, let's read the question and find out. So initially you start with a score of 1. You want to maximize your score by applying the following operation at most k times, right? So k is the number of operations you can make, and we can notice that because k is so large, like it could be 10 to the power of 9, right? So you can't do each operation on its own. Like either we have like some log n way of doing it, or like we have to combine operations somehow. Yeah, so we can choose any non-empty subarray. So L to R, they haven't chosen previously. You can choose an element X with the highest prime score. What is prime score though? Yeah, so prime score of an integer X is equal to the number of distinct prime factors of X. So for example, prime score of 300 is 3. Because wait, what? For example, is 3. It's equal number of distinct prime factors. Okay, right. I see. Right. So like 300 has 3 prime factors, so that's why the score is 3. So that's what prime score is. Right. Wait. So, but I'm not sure what we can pick, like with L and R. Oh, but it has to be something that you haven't chosen previously. Okay. So you want to. So that's where the like this thing comes from, cause like you have that many amount of ranges that you can choose. Right. So if multiple such elements exist, you want to choose the one with the smallest index. Okay. And you want to multiply your score by x. Wait, you want to multiply it by x? Right. So you're not just adding it; you're multiplying it. Um. Well, I guess we always want to go with the largest one first. Um. Let's finish reading the question first. So that denotes a subarray of nums. So starting at index L and ending at index R, and both of them are inclusive. Does it say anything about L and R? Wait. Wait, divided by 2. Why is it n times n plus 1, not n minus 1 times n? Because, like, don't you have, like, n choices for L, and then you have, like, n minus 1 for R, but then you have to, like, swap them around. I'm really confused on the bound. Maybe I'm tripping. Yeah, because they're inclusive, right? And obviously, like, L and R has to be, well, within bounds. So the prime score, maximum possible score, and then like we want to modulo it because it could be very large. So if k is 2 here, well, I think like we definitely need a quick way to find all the prime scores for each number. So I think to do that, like because it is only 100,000, we can use Siev's algorithm to find the number of primes. When I cook that up, it will be very clear. The other observation we have to make is let's say we have found a should I draw it out? Yeah, so let's say we have found, I don't know, maybe it was 2 times 3 times 5, 30. So obviously 30 has the most, like, has the highest prime score, right? So we want to, like, just go with every every subarray that contains it, right? So we want to use those first. So that will be these, right? So we want to use that up first. And then we can like use the other one. So wait, what if we turn this into 6? We probably would wait, actually that's not all of them. We also have this, and then we also have something like this, right? Yeah, so basically, like, all these subarrays that contains 30, we want to use that up first, like in our K operations, because, well, we can always choose this, right? Wait, but it says, like, if multiple such elements exist, choose the one with the smallest index. I'm not sure why you would do that, like why you need to do that. Oh, because you want to multiply your score by x. Choose an element x. Wait a second. So is it that the larger the number, the better? Is that true? So choose an element x with the highest prime score. So here, wait, multiply your score by x. Yeah, so wait, actually, it does matter. It doesn't matter how large your number is as well. Right, so, like, let's say, between, like, 30 and 300, we want to go 300 first. And we don't actually want to include 30 in any of the in any of the subarrays, because like, they have the same prime score, but we want the larger number, right? So in this case, like, we'll go with this, go with that, and then this, to basically avoid like choosing 30 at all. Yeah, but we definitely need a fast way to do this as well. So that we don't like, because K is very large, like, we can be doing a lot of operations. So we might even need a quick way of, like, squaring or yeah, of, like, multiplying numbers, well, squaring numbers modulo like this, because, like let's say we want to, like, let's say we have to multiply, like, 300 like 10,000 times, right? It will definitely be way too slow if we, like, do the normal way. So I remember there's a math algorithm that precisely does this. And it just, like, quickly finds the modulo. Is it LeetCode Fermi? I forgot what it is called, but I definitely will need to search that up, because I don't remember the formula. Right. So yeah, so, well, that's the, like, that's kind of like the first observation. I realized I didn't show the my working out. So yeah, so that's the first observation. So we want to always start with the biggest number. Wait, we want to multiply the largest number first. So actually, if we have, like, I don't know, like 1024 here, well, yes, the prime score is very low, but we want to multiply this number as much as possible, right? So, oh, wait, actually, I have an idea. So let's say like we have 1024 here. Well, the prime score of this is just going to be 1, right? Because this is 2 to the power of 10. Um, so that means, like in the subarrays that we are going to do, we we don't we don't want to include anything that that has the same uh prime score or a larger prime score, right? Because like otherwise we are not going to be picking like 1024. Well, this is assuming that 1024 is currently the largest number. And also, yeah, so if multiple elements have the same prime score, we want to choose the one with the smallest index, right? So that means it is not okay if we are including numbers with the same prime score on the left, but it is okay if we include the same, like the numbers with the same prime score on the right. Yeah, but we definitely also need a quick way. So like if we have a prime score array or something like that, we need a quick way to find, well, like where the where the next larger prime score is. So if the prime score is 1 here, like we have a bunch of 1s, and then like we can have a 2 or like a 3. So we need to know the position of this quickly as well. And then for going backwards, let's turn that prime score into like 2. So we can have like 1 1 and then like 2, something like that. We need to know like the closest one that is like equal or larger. So we know that we don't want to include that. Right. So this behavior, we can use a stack for it. But I think basically if we do that, and then we just go from the largest number, like to the second largest, to like third largest, like until we run out of operations, I think that'll work. So, so what we need to do, well, the first thing we need to find the prime score. I should start coding actually. Yeah, let's just code it out honestly. So the first thing we have to do is we have to find the prime scores, and then so prime scores, let's set it as I don't know, like 0, like 0 for all the numbers. So let's just set n to be equal to length nums. So range n, prime scores. Yeah, and so prime score. Basically we're just gonna map the. Oh wait, actually we want 100,001 here because we are storing the prime scores for all the numbers like from 1 to like 10 to the power of 5, right? So that's what we should do instead. Right, and then what we want to do is let me think about it. Yeah, so for num in range, I think also 100,001. We'll name this something better, like so max. Yeah, max num. We set it as this. We set it as this, and then we can just do like range max num plus 1. So max num plus 1. Wait, actually, I think would it be better if we find all the primes first? Actually, if we find all the primes, and then like we can just go through, like let's say like 2 is a prime, right? We can just like add 1 to like 2, 4, 6, 8, 10, and so on, and then 3 it'll add that. And there's a very well known time complexity for this is n log n, because like this series like if it is 1 over all the primes and so on, this series is, I think it's like log n, and well, you have to like, yeah, I'm pretty sure it's log n because of this. I forgot what this series is called, like some prime, but this is well known. Like, but my point is, it won't time out. So yeah, actually, let's find all the primes first. Wait, actually, before I forget, I should mark down what I need for my algorithm. So we want to find all the prime scores, and then we want to find so we want to go from the largest number to the smallest, right? So we want to find well, largest number to smallest. Wait, yeah, we can like make the map. Yeah, like basically like we have to make an index map that goes from largest to smallest num for nums. So we need to do that, and then we also need to wait, let's look here. We need to find out like the closest prime scores. So find prime score bounds. So left, find index. So we want to find the index with equal or larger prime score, and for the right bound, we want to find the index with larger prime. I say probably like closest. Yeah, so we want to find the closest. So after we find that, we can actually like start applying operations. But there's one more thing we need. Need a quick way to calculate like a to the power of p b mod x. So we need a quick way of doing that. And also, before I forget, I'm gonna add this in. And so basically we're just gonna write a function that does this for us. Right. So I think we have our layout is correct, I think, but we just have to code out each of these things now, and we also have to find out how to do this, of course. Yeah, there's a log n way of doing this, I'm pretty sure. We just have to find out. Right. So prime scores. Oops. Oh wait, I think I remember this. So the trick is, let's say you have like 3 to the power of 8. Well, you can turn it into 3 to the power of 2, and then that to the power of 2, that to the power of 2, right? So like, because this is equal to this, and that converts into that. So that means we can, and I think like when we modulo it, so like if we find the modulo of this, and then we square it, it will still be the same. Like, and my point is like if you evaluate like
3 to the power of 2, you modulo it like to some x, and then square it, and then modulo it, that's going to equal, well, mod x, that's going to equal to, well, 3 to the power of 2, and then you do the same, and then mod x. I'm pretty sure that's the case. I'm pretty sure. But yeah, we can just do that. So we just have to turn our exponent into like some binary number, and we can like find out like when we have to square and when we don't have to square. Wait, actually, let's find out right now. So let's say we have like 3 to the power of 3. So we start with 3 to the power of 1. Well, we obviously, well, this is like 1 and 1, right? Like in binary. So, wait. So 0 be 1 1. Yeah, so when we have 3 to the power of 1, well, we also do want to remember the previous value, and I'll show you why very soon. But yeah, basically, so we can turn this into, we can just square this, and then like that basically shifts the bits 1 over, right? So that's why we have like like the binary like 1 0. So we have binary 1 here. So we can just square that. So that'll work. But now we want 0b11, right? Well, what is that equal to? That's just 0b10 times 3 to the power of 0b1, right? So like in decimal point like terms, it would just be this. Yeah, so that's why you have to remember the previous value. But that should work. Yeah, so oops. So we just need to like do like the binary thing, and that's actually where log n comes from as well. Yeah, so we have everything figured out now. So well, the only thing left to do is actually coding the stuff out. So I guess we can do like is prime. We'll just do true for everything for now. In range max num plus 1. So we want to find out find all primes from 2 to max num, and yeah, and 0 and 1 is going to have a score of 0, so we just like don't worry about it. Yeah, like 1 is not a prime number. Like we should all remember that. Is 0 a prime number? 0 is definitely also not a prime number. Okay, so final primes. What we can do is so for I in range, so we want to start at 2, and then we want to go all the way to max num, right? So that's why we need the plus 1, because it is inclusive. So if is prime I, so if I is prime, what we want to do, we want to go from I all the way to max num plus 1, but we want to step SI, so like basically it would be like 2 4 6 8 all the way like to 100,000. If I is like 7, it is just going to go like 7 14 and so on. So we want to set all of them into false, because well they're not primes. Like it is a multiple of another prime. And otherwise we just don't do anything.
So that's going to give us all the prime numbers. So like it'll be true for all of those. Guess we should also manually do this just for safety. So we set that to false. We'll put it here. I think it's a tiny bit nicer. So final primes to maximum. Right, so now what we need to do, we have to calculate prime scores. So for each of the prime, so for again we just do this maximum plus 1. So if I is a prime number, well, we just want to like go to each of the prime scores. Wait, actually, yeah, we have to do the loop again. We just, so for all the prime scores, we want to add 1. Well, so like for all the so let's say like when I is 2, right? So for all the multiples of 2, we want to add the prime scores of them by 1, because, well, 2 is a prime number, right? So when we go to 3, it's going to do the same. When we go to 5, it's going to do the same. But if I is not a prime, it wouldn't do this. And again, like this is n log n, as we have mentioned before. Yeah, so that's how we get all the prime scores here. Right, so we got the prime scores now. Now we need the quick way to calculate like a to the power of b mod x. So I think we can call it like fast pow. Is there a Python? Let me check if there's a Python like built-in function for this actually. So fast exponents, Python with modulo. If it is implemented, then we don't need it. Wait, so yeah, so the built-in thing is power, right? But yeah, what is the one with modular? Oh, so you just add the modulo as the third argument. Well, does it calculate it in fast way though? So yeah, I'm just gonna search up the time complexity of, well, so what it's saying is like pow abx is gonna give us the answer. But if this is on, it's too slow, right? So we have to find out the time complexity of that Python built-in function. So just do time complexity for Python pow with modulo. So let's see if Python is smart and does it in the log way. Apparently it does. Well, we can test it out. Let's do something like I don't know, 100,000. Well, we can make this number very large, and if this works, then that means, well, if this doesn't time out, that means it does use a modulo for this, and we don't have to implement our own, which is actually extremely good. Right, just return -1 here. Yeah, let's see, is Python smart? Oh, turns out Python is smart. Yeah, so we can just use the built-in power function. So we don't actually need this, which is awesome. Yeah, every day we learn new things. So yeah, we don't need that. Just get rid of this because that's built in. We can also remove this guy up here. So now we have calculated the prime scores. We have calculated we know the prime scores of like each of the possible numbers. I think it's time to do this step, which is like find the left and right score, like the closest left and right element that like has a equal prime score or higher. I guess we can yeah, I think we should have a map that basically like stores the prime scores first. It's just a bit easier to deal with. Actually, we don't need that. We don't need that. Right. Let's make this first. So so we can do something like nums with index. Just call nums index. So we can do. So we want the num first. So nums. So we want the actual number, and then we want the index. For index num in enumerate nums, and then we want to sort nums in reversed order. Well, actually, if we have two, like let's say we have the two largest elements, like 1024, it doesn't really matter which way you go first, right? Because like let's say we can only like consider, I don't know, like this amount of ranges, but this one we can consider like all of them. So like when we are looking at this, well, because they have the same prime score, it will include like 1024, and like basically that means like it is going to include everything anyways, like no matter which one we do first. So yeah, we can just sort it. I think it's reverse equals true. I think that's how you do it. I'm just gonna print it out because I don't remember. I think it's reverse true. It's not. Is it reverse? Oops. What did I do wrong? Printing the wrong thing. That's what I'm doing wrong. Yeah. So while that is running, well, we can. Well, actually, we just need this, right? And we just start from like 0. Yeah. So this is gonna work. That's gonna work. And like basically like during this loop, we just want to do for like something like for num. Wait, do we need that? Yeah, something like for index in nums index. So that's gonna give us the index we want. I guess we still need num because we need to multiply that, right? So we have the result, which is we will start at 1, and then like we'll do a bunch of like stuff here until either we run out of operations or we run out of like numbers. Wait, will we ever run out of operations? I don't think so, right? Because of how this is set up. Wait, actually that's not true because it could be 10 to the power of 9 as well. Okay, yeah, but that means we just have to check either way. We should get back to actually coding stuff. I'm just yapping so much. So left and right. So let's do right first. Right should be a bit easier. So we need a stack. And basically, so for for I in range nums. So now we want the actual numbers. So we want the prime score for that. Well, that's just gonna be prime scores of Actually, let's do enumerate instead. Enumerate num. So we want the prime score for our current like number, and so we want to what do we want to put on the stack? That's also a question. But like definitely at the end we have to put our nums in, right? So yeah, so stack append. Yeah, definitely need to put this. And yeah, actually let's go back here. So let's say the prime scores are something like 2112, right? So if we are starting, like, we have a stack, so we should store, I think we should store the prime score, and then we should store the index, so that'll be 0, and then when we look at 1, well, that's just gonna, like, add 1 in, and then the index is 1. Yeah. And then when we look at this, well, this is like 1 and 2, right? So like that will be num and index. But it has the same score. Well, actually, same score is fine when we are going to the right. So we just want to add that in. But lastly, when we have this guy, so we have 2 and 3. So when we compare the prime score with the top element, well, this is larger, right? So that means this is also like the first thing we see that's larger. So for the second element, we can put I guess like we can find out how many numbers we can go to the right. So like in this case, well, there are no numbers. Like we can't go any further to the right. So we need another array, like something like I'll just call it right for now. So we have like 4 elements, right? So like because this is smaller, like because 1 2 is smaller, we can just put 0 here. Well, because we don't have any elements here, so that will be like 3 minus 2 minus 1, because we want to exclude the first number that has a larger prime score. And then so we keep going down, so we see 1 and 1. Yeah, so 1 and 1 again, it is like the prime score is larger, like our current element is larger. So we want to do 1 now. And then when we go here, well, that's the same score. So now we want to like add that there. And like of course we have like if we have like 3 like there, we just keep popping. But let's ignore the 3, like let's ignore that for now. We should think about what to do for the like remaining element in the stack. Well, actually, we just want to get the size of the size of the like nums array, and like because we have to end here like anyways, right? So like we can just do the same thing, right? So we have like 4 minus 3, so like 4 minus 3, but we are not actually including like the like because there's nothing, right? So we're not including that, so that will be 0 as well. But then so we want to pop that, and then like for this one, well, so like we have 3 elements, right? So like we'll do 3 here, and something similar we can do that for left, and that should give us the answer. So yeah, so we have a stack, and guess we can initialize left and right as well.
So we just want to set it as some placeholder for now. So -1 for just do none. So none for something in range. I think the length of nums, right? And then we do that for right as well. Yeah, we're guaranteed to get an answer for each of them, because like either we found a larger element or at the end it is in the stack, and we can like add that in. So wait, yeah, so instead of the actual num, we want the prime score instead, and we want the index of that. So right, so we get the prime score. Yeah, so while stack, so while there are still elements in the stack, and the current prime score, if it is well, when we're going to the right, it has to be strictly larger. Stack -1, so the top element, and the 0th thing, so that will give us the prime score. So we want to do like old score and old index, so that's going to be equal to stack.pop. So we're going to get the top, and then we just want to like put the information into like the right array. So we'll do right. Well, it'll be at the old index, right? That we actually want to put in. So if we go back here, we can see, like when we are popping, like when we add 3 in, like when we add the third element in, like we will look at the index. So that's how you know which one we're dealing with, and then we can like we can just do just find the number of elements by like just subtracting, like finding the difference. So it will be the current index minus the old index, but then we don't want we don't want to count either the current index or the old index. We want to count how many elements are between. So that's why we have the -1 here. So we're gonna do that until like we don't pop any more stuff, and we'll finish. So now just want to do while stack. Again, we can just do score index. We do stack.pop. So right, index is going to be equal, well, to the length of nums, minus the index -1. Yeah, so that's like if there are no larger elements on the right, and we can basically just copy the exact same thing for left, which is very convenient, right? Yeah, we want to. We can't just copy it. We have to we want to reverse now. So well, actually, if you reverse nums, wait. I have a very clean idea actually. So if we do reverse nums here, so all the nums are going to like, it's going to be flipped over. This is a terrible example because it is a palindrome. But let's say like for this example, if it is flipped over, we do the same thing, but then, so like, let's say for this, right? If we flip it, 6 to 30 and 3. If we still find the score, so like let's say for 300, it's going to like give you, like it's going to have a prime score of 3, and then like we do 0, prime score of 2 here, prime score of 1, 1, 2, and then like when we get here, well, it has a prime score of 3, right? Because this is like 2 times 3 times 5. Yeah, so that's what we have. we're gonna like look at, well, it will pop all the elements because when we're going to the left, it is it is like we like equal or greater. We will still like we want to find the closest element that's equal or greater, like for prime scores, right? Um, but if you notice, like if we do the minus here, it's still gonna give us, well, how many elements on the right? Well, in the actual array, it will be on the left, and so like we're gonna like get all the scores, and if we just reverse that, um, like if we just reverse that at the end, it's just gonna give us like what's on the left. So we can do that. Um, so prime nums, but we should do this instead now. While stack will do the exact same thing, but then we should change that to left. Yeah, and while stack. So we want to do that, and then we want left to be equal to the reversed of itself. So that's what we are gonna do. And yeah, I think we're getting very close. So result is equal to 1. So for num index, so that's gonna be the sorted nums index, right? So in this case, well, we're going to look at we're going to look at 300 first. And we want to find out how many times we can actually multiply, right? Wait, actually, I don't think we should do -1 here, and I'll give a reason to that. So, if there are no elements, like because what we want is, let's say we have 300. And let's say like we have 2 elements here and 1 element here. Well, how many subarrays can we form? Well, we can form well, let's say there are like A elements here, B elements here. Well, we can choose like from 0 to A elements on this side, and we can choose 0 to B. So that means the number of like subarrays we can choose is just A plus 1 times B plus 1. So actually we do have to consider like not having any elements. So why don't we just like get rid of the -1? It looks a bit nicer as well anyways. So number of subarrays. So subarray, we'll set it to, so one left index. Yeah, so we want that multiplied by right of index. So that's going to give us the number of subarrays. So that's also the amount of times we want to multiply our current number with. So we want like this to be multiplied by that, but then we have the mod. But after we multiply like this number, we have to mod it again, because wait, let's just do this. Actually, this is a bit clearer. So we are multiplying the current result like with whatever, like however times we have to multiply like the current number and like the number of ways, right? Like modulo, of course. But then this number could get too big as well, so that's why you need the modulo here. And I think if we return result, and if I'm on a super good day, I'm not on a super good day. Okay, let's see. Let's reverse iterator. Yeah, so we just have to turn that back into a list.
Whoa, that's extremely large. Wait, why is that? Oh, of course, I have to consider the number of times we can actually do like operations. So remaining operations we set it as k. So now if k is 0, we just want to return the results. Like we don't want to do any more stuff. Otherwise, we should take the minimum of should be remaining operations. So either we do like left times right amount of operations, or we just choose like we just do all the remaining operations, right? So whatever is whatever is like smaller, and actually we just do this. That's nicer as well, cause now we just do this minus left index times right index. So like if the number of remaining operations is smaller, then we can just end, right? So I think it should work now. Oh, I got the first case, not the second. Right, let's see what I'm doing wrong. So what they chose is so I think you would choose 19 first for sure. Yeah, actually, let's let's print the number of operations for each of these. I think that will be helpful as well. Let's write index, and let's print number and index. We just do this so we know what values they actually take. I think that's helpful as well. Yeah, so we have 19. So the index is 0 left. Wait, left is 1 and right is 6. I forgot to do the prime scores, didn't I? Prime score. Wait, I did put the prime score though. Wait, so the prime score for... So this is like going to the right. Yeah, something is terribly wrong here. So I need to fix that. So for index... so that's going to be, like, if we're looking at this, it's going to be 0 and 19. So we're going to have 19 here. So we will get the prime score. It should be... I should print the prime scores, honestly. Because if I messed up there, this would be wrong as well. So prime scores... print. Let's print that. We can just check like the first 20 and just make sure. Oh yeah, see, this is where it has gone very wrong, and we should find out where. So, yeah. What about is prime though? Is that? Yeah, let's print out is prime. So it's prime. We want to print that. How did all of them got turned into false? Yeah, so we initially set it as true. We turned the first two into false. I see. So when I do this, let's say like I is 2, right? It will turn 2 into false as well, even though 2 itself is a prime. So we want to like turn everything else, basically. Yeah, but in this case, we do want to multiply. We want to add prime scores here. Yeah, okay. So it works now. Are we printing any stuff? Yeah, we should. Let's run it. I'm like 60% confident it works. But let's see. It's quite slow. Maybe the power thing is like, what's for such a small case as well? Okay, that means I'm for sure doing something wrong here. Let's add this case in. So what do we have here? We have like, are the ones causing the problems? Wait, it could be, right? Yeah, it could be the ones causing problems. Cause like this case is very small, so yeah, time limit exceeded here is very strange. Yeah, let's see if we have gotten up to let's see if we've gotten up to like this point without like timing out. Okay, yeah. Yep. So we want to do that. Yeah, the unfortunate thing is I think if time limit exceeds, it doesn't actually show you the standard output. Huh? Huh? What's Wait, what? Wait, I got the correct answer. But then it says time limit exceeded. Is my program just way too slow or something? Like to pass all the test cases. Wait, now I'm like really confused. Maybe we should analyze the. Yeah, okay, so they put a time limit on like every single test. That's kind of annoying. Yeah, n log n, that makes sense because it is n log n. How do I optimize this though? Yeah. Oh, we have like back-to-back optimization that we have to do, which is quite annoying, honestly. Maybe this is slow. Nah, but none of them should be so slow that like it ruins the time complexity, right? And like left and right, well, it doesn't matter because like this number can be as big as possible. Because like we are gonna take the log of this anyways. So mod. I need to squeeze time, but I don't quite know how. Are people saying like Python is not working or something? Let's see. Let us see. I do agree. I think this is an extremely good problem. Yeah, this is what we get. Yeah, but I think I know why. Because like we are doing this every okay, I think I see the problem. So if you're running it by itself, it wouldn't time out. But because for each of these cases, we are doing like we are finding the prime scores for like all the numbers, and it doesn't have any cache, right? So that's why like this case is so tiny, but like the overall time got timed out. Right. So what we should do here is we should just find the maximum of nums. I think that would be more like economical. I think. Does that work? Or does it still time out? Okay, yeah, it doesn't time out anymore. Yeah, so that is my suspicion. Yeah. But yeah, honestly, this problem, I think this problem is really a really good problem. Like, you have like you have to know how to like find the primes. Like you have to find the prime scores. Like for that, you needed to know the fast way of finding all the primes. Um, and then you have to notice that you want to like go from the largest to smallest. You have to find the next element, or like the closest previous element that has the same or like larger prime score, depending on which way you go. Uh, and then obviously like you have to notice that like uh when you're doing exponents with mod, there's actually a log-n way of doing it. But yeah, um, this is a hard problem. Well, compared to yesterday's one, like this one is definitely a hard. But also just a really good question. So yeah, um, yeah, and I think I took like an hour to solve this. But yeah, thanks for watching. If you've gotten to the end, I don't know what to say. Thanks for watching and staying for a whole hour, because I wouldn't know. Like I don't think I'll have that attention span to stay that long. But yeah, thank you so much for watching, and I'll see you tomorrow. Bye.